Welcome to lecture 5.1 on inverse functions. Looking at is how do we determine whether a function is one-to-one, and if it is, to find a formula for its inverse. We're also going to simplify expressions of the type f of f negative 1x, and we're going to learn about this notation as well. Notice, remember, this notation is a composite function. The function f composed of its inverse function. That's what this f negative 1, we're going to look at that. And notice that it's interchangeable. We're going to learn how to find the composite of a function with its inverse or the inverse with its function. When we go from the output of a function back to its input or inputs, we get an inverse relationship, okay? So, we have an input to a function and an output by definition. If we then take the output of a function and put it into its inverse function, the output from the inverse then comes back to the input, okay? It's a little bit confusing, but here's a couple examples. So for example, subtraction and addition are inverse operations, okay? So if our function was adding 2, the inverse of adding 2 would be to subtract 2. And notice if we put an input of 4 into our function and added 2, we would get 4 plus 2. And then if we subtracted 2, we'd get back to that same input of 4. Okay, so if x was 4, 4 plus 2 is 6. That's our output. Minus 2 gives us back to that same input. So it's kind of a loop. Conceptually, you might think of it like tying and untying a shoe. If you tie your shoe and then you untie it, you're back to an untied shoe. Okay, so it's just a loop, if you will. A function, its inverse undoes whatever the function does. So if my function was tying, the inverse function would be untying. If my function was subtraction, the inverse would be addition, and vice versa, and vice versa. Okay, when that relationship is a function, we also have an inverse function, okay? If a relation is a function, then we have an inverse function. To find the inverse relationship, we interchange the first and second coordinates of each ordered pair, or we swap the x and the y coordinates of each ordered pair, and this new set of ordered pair creates the inverse relationship. So for example, if I have a function or a relationship h, which has these points, negative 8, 5, 4, negative 2, negative 7, 1, and 3.8, comma 6.2. Again, this 3.8 is x, 6.2 is y, the same in all of those ordered pairs. Then the inverse of the relationship h is given by the opposite. Notice what we've done is we've swapped x and y. So the first point would be 5, negative 8. The x becomes y and the y becomes x. Negative 2, 4. 1, negative 7, 6.2, 3.8. Okay, so it's pretty easy to find an inverse relationship or the inverse function or the inverse graph simply by switching the x and the y coordinates. Simply by switching the x and the y coordinates. An inverse relationship, interchanging the first and second coordinates of each ordered pair in a relationship, produces the inverse relation. Consider the relation g given by g equals 2, 4, negative 1, 3, negative 2, 0. Graph the relation in blue and find the inverse and graph it in red. Well, the inverse of the relationship is just swapping out the x and the y, switching the roles. So instead of 2, 4, we get 4, 2, 3, negative 1, 0, negative 2. You can see here the original relationship g is in blue, the 3 coordinates, and the inverse are in red, these 3 coordinates, okay? What these are a reflection of the pairs in g across the line, this diagonal y equals x that you see here. So it's a reflection across the diagonal. It's a little bit confusing and not always easy to see this. I always jokingly tell students that it's kind of like that Beyonce song, Put a Ring on It, where she turns her hand a quarter way and then flips it over. If you rotate the graph a quarter clockwise and then flip it, you'll get the inverse relationship or graph. And I'll show you that in a minute with a better graph than just with points. If a relation is defined by an equation, interchanging the variables produces an equation of the inverse relationship. So if we have points, we just switch the x and y values in the points. If we have an equation, we're going to do the same thing, but we're going to switch the variables, the x and the y, for each other. For example, find an equation for the inverse of the relation y equals x squared minus 2x. So there's a couple steps we're going to go through here, and I'm going to go through them step by step. The first thing we do is we interchange x and y, and we obtain an equation of the inverse. So wherever we have an y, we're going to replace it with x. Wherever we have an x, we're going to replace it with y. And this gives us the inverse relationship. Okay? The graph of a relation and its inverse are always reflections of each other across the line y equals x, as we saw in the last graph. Graphs of a relation and its inverse. If a relation is given by an equation, then the solutions of the inverse can be found from those of the original equation by interchanging the first and second coordinates of each ordered pair. Thus, the graphs of a relation and its inverse are always reflections of each other's across the line y equals x. For example, if I have a function y equals x squared minus 5x, and I want its inverse, all I have to do is swap the x and the y values. We can see that here, and we can see it also in terms of the equation. Where I had y, I now have x. Where I have x, I now have y. Where I had x, y coordinates, I now have x, y coordinates by swapping the order. Okay? Excuse me. And so here you can see the graph of the original relationship, which was a quadratic function. If we rotated this a quarter to the clockwise, notice we'd have a sideways parabola, and then if we flipped it, it would go from the bottom to the top. Rotate a quarter to the right or clockwise, and then flip it over the x-axis. One-to-one functions. A function is one-to-one if different inputs have different outputs. Okay, remember that when we were talking about functions, the definition of a function is that you have a consistent output. Every time you put the same number in, you get the same output out. Okay, now we're going to define them a little bit more restrictively, that a subset of functions is some functions are one-to-one and some are not. A one-to-one function, every point has its own unique output. Functions can share outputs, but then they're not one-to-one. Okay, so what this is saying is if our input A is not equal to B, then we cannot have the y value, these are x values, then the y value cannot be equal as well, the y values. So if our inputs are different, then the outputs are different, and that's how we know it's one-to-one. One-to-one has a unique answer for every input, a unique output for every input. So we could also say this, a function is one-to-one if when the outputs are the same, then the inputs have to be the same as well. So if we have a function who has two different, or who has two answers, two y values that are the same, then we know that the input, the x values, have to be the same if it is one-to-one. Okay? So like we talked about before, all functions by definition are SISO. When you put the same input in, you get the same output. And that's just about them being consistent. You want a function to be consistent. When you pump gas and the function is calculating how much money you owe, you don't want, today you pump 10 gallons and tomorrow you pump another 10 gallons. You don't want the outputs to be different. The function is the same, assuming the price of the gas is the same. Some functions, however, are DISO. For a different input, you have the same output. and this is shared outputs, and that is allowed, right? You might think of your cell phone, okay? Most cell phone plans have a gigabyte or a data limit. So let's say your cell phone plan has comes with 5 gigabytes of data. Well, your monthly cost, if you use 3 gigabytes of data, if 3 is your input, the input is the number of gigabytes of data, well, the output is going to be that same $30, let's say, for up to 5 gigabytes. If you use 4 gigabytes, your cost is still going to be 30. If you use 5 gigabytes, your cost is going to still be 30. But as soon as you hit 6, then you're going to have a different one. But notice that 0 through 5 in that example all have the same output because your cost of your cell phone doesn't change because you stayed within the limits. But it's still a function, okay? So with different inputs, they can have the same output. But DSO is not a one-to-one function. If it's DSO, different input, same output, then by definition it is not one-to-one, because in a one-to-one function, every input has its own unique output. So 1, 2, 3, 4, 5 would all have to have different outputs in order for it to be one-to-one. So one-to-one functions are what we call dido. For each different input, there is a different output. You can't have 130 and 230, etc. That might still be a function, but it wouldn't be a one-to-one function. Okay? A one-to-one function has no shared outputs. No two inputs create the same output. If the inverse of a function, f, is also a function, it is named f inverse. Okay? It looks like a -1 exponent, but it is not an exponent. It's read f inverse. When you have a -1 exponent on the function notation, this is read as the inverse of f or f inverse. Again, the -1 is not an exponent. It does not mean the reciprocal of f. It is not equal to 1 over f of x. Okay? It's very clear, it's very important that you get this, that this is just notation on a function. It's not f raised to the -1 power, it's f inverse. The -1 is just indicating that we have an inverse. Okay? If a function is one-to-one, then its inverse, f inverse, is also a function. Okay? Now remember that when we were talking about functions before, we had two vocabulary words, domain, which was the set of all inputs or the x values, and range was the set of all outputs or all the y values. Okay, so that will help us with some of these other rules here. So the domain of a one-to-one function f is the range of the inverse, f inverse, right? Well, that makes sense because remember, how did we find the inverse? We swapped x's and y's. So the domain for the original function becomes the range because the x now becomes y and the x and the y becomes x. And that's all the second one is saying. So that makes some logical sense. The way we find an inverse is to swap the x and y values. So of course the domain and range are going to swap as well. A function that is increasing over its entire domain or is decreasing over its entire domain is a one-to-one function. So if it's constantly going up or constantly going down, it is a one-to-one function. When we were testing functions, we used something called the vertical line test to see if a graph was a function. Well, there's a horizontal line test to see if a function is a one-to-one function. If it is possible for a horizontal line to intersect the graph of a function more than once, then the function is not one-to-one and its inverse is not a function. So we do the vertical line test first to see if we have a function. We do the horizontal line test to see if we have a one-to-one function. Okay? Here we have a function because when we do the vertical line test, we see it only touches once. But notice that when we do a horizontal line, it touches in two different places. It touches more than once. So this is not a one-to-one function. It is a function, but it's not a one-to-one function. Here, because this is not a one-to-one function, when we take its inverse, remember we rotate it a quarter to the right or clockwise and flip it, we get this function. And notice the inverse is not a function. So if a function is not one-to-one, then its inverse is not a function. Okay? In order for the inverse to be a function, the original function has to be one-to-one and pass the horizontal line test, meaning that any horizontal line can touch at most one point. Let's look at a couple of these. From the graphs below, determine whether each function is one-to-one and thus has an inverse that is also a function. We can see here that no horizontal line intersects more than once, so this is a one-to-one function, and its inverse would be a function. Okay, the horizontal line only touches at one point, so f of x is a one-to-one, and its inverse is a function. Let's look at B. Here, a horizontal line touches more than once, so it is not a function. Not one-to-one. The horizontal line test is for one-to-one functions. And if it's not one-to-one, then the inverse, or f inverse, is not a function. Okay? If it touches more than once, a horizontal line touches more than once, then it's not a one-to-one, and its inverse is not a function. You can see that that's exactly the same example. A couple more just to get the feel. Horizontal line touches one place. So it intersects. No horizontal line intersects more than once. It only touches at one point. So this is a one-to-one function, and its inverse is a function. Here we can see a horizontal line is touching actually 3 places. So the horizontal line intersects more than once. It is not one-to-one. The inverse is not a function. Okay, that's the horizontal line test. How do we obtain a formula for the inverse? Okay, if a function is one-to-one, a formula for its inverse can generally be found as follows. Okay, so let's look at an example and at the steps. So here we have a linear equation. A linear equation by definition, unless it's a horizontal line, which would be f of x equals a constant, is a function, and it's also one-to-one. The first thing we're going to do is replace the function notation with its variable y. Very simple. Just replace f of x with y. The second thing we're going to do is interchange x and y. This is what we've been doing all along to find the inverse. Wherever we have a y, we turn it into an x. Wherever we have an x, we turn it into a y. Then we're going to simply solve this equation for y. That means rewrite it as y equals. And if we do that, we get y equals 1/2 x plus 2. We'd add 4 to both sides and then divide both sides by 2, and we'd get 1/2 x plus 2. The last step is just to put it back into functional notation. And again, now we replace y with the inverse of f inverse. Okay, so now we have the inverse relation in functional notation. So again, these steps are: we replace f of x with y, we interchange x's and y's, we solve for y, and then we put the notation back in place by using the f inverse notation. So let's do one of these. Determine whether the function f of x equals 2x minus 3 is one-to-one, and if it is, find a formula for f inverse x. Again, we have a linear equation, so we know that it is one-to-one. It passes the horizontal line test, and its inverse is a function. So now again, we go through those 4 steps. The first step is to replace f of x with y. Then it's to swap out the x's and y's, change every y into x and every x into y. Then we solve this equation for y. And then the last step is to replace it with the notation for f inverse. And here's our formula for the inverse function. Okay, very simple steps. Replace f of x with y, the notation of functional notation with the variable y. Swap out x and y, turn x's into y's and y's into x's. Solve for y, and then replace y back with the notation for an inverse function. Graph f of x equals 2x minus 3 and f inverse of x equals x plus 3 over 2 using the same set of axes, then compare the two graphs. This is just saying graph them both and put them on the same graph sheet, if you will. Okay. The solutions of the inverse can be found from those of the original function by interchanging the first and second coordinates of each ordered pair. This is how we started with the inverse. So let's find some ordered pairs for f of x, and then just switch the x's and y values. And that's what we've done here. We found this is pretty simple linear equation, plug in x and find y. And then these same 4 points we can use for the inverse by just swapping out. Here's y, becomes x. Here's x, becomes y. So we just have these inverse points. Here we can graph them. And again, we see that it is a reflection across the diagonal y equals x. Okay. And as we know that by definition, the graph of an inverse is a reflection of the graph of the function across the line y equals x. Inverse functions and composition. Okay, composition tends to be a little bit difficult, and we did this, I believe, in chapter 2. Remember, this is the composite of the f inverse with f of x, the original function. Remember, what comes last is the input to the what comes first. So this is f inverse with the original function as its input. And what's key here, again, remember that when we composite this, a composite means we just take the output of one and put it into the other. We get back to the original input. And that's how we started with this idea of what a inverse function is. Okay. So if we do the composite function of f inverse of f, we should get back to the answer simply x. And this has to work no matter which order we do this. If it's the composite of f with its inverse versus its inverse with f, we still get that same x value. And so if we're trying to test two functions to see if they are inverses, we composite them one on the other in both directions and make sure that our answer to that is indeed x. Okay? So the composite of a function with its inverse will always equal x. If it doesn't equal x, then they are not inverse functions. Given that f of x equals 5x plus 8, use composition of functions to show that f inverse x equals x minus 8 over 5. So we're trying to test that these indeed are inverse functions. And so what we're going to do is do the composite. Okay. Now I know this was a challenging section. So again, the inverse with f of x as its input. So here's our inverse. Now remember, what we do is we replace, when we're doing this composite, wherever we had an x, we are going to replace with the formula for f of x. So in this first one, we're going to replace this x with 5x plus 8 in parentheses. And we always put the replacement in parentheses just to make sure if we have to do any distribution or raise it to a power, etc., that we handle that. Okay? So again, this is saying the inverse function, instead of with x, we put in the formula for f of x, which was 5x plus 8, and then we substitute it in. So where we had x, we now have 5x plus 8 minus 8 over 5, and then we simplify. Well, 5x plus 8 minus 8 is simply 5x over 5. 5x over 5, the 5's cancel out, and we do indeed get x. Now we do have to check it in both directions. So now we have the function with the inverse function, inverse of f, as its input, which this means the function f with the formula for the inverse going to be used instead of x. So where we had x here in the function, we're now going to replace with this fraction, x minus 8 over 5. Okay, again, 5 times x now becomes 5 times the inverse value, the inverse formula, x minus 8 over 5 plus 8. Well, we can see here, because fractions are division, and division is the inverse of multiplication, these will cancel out, because this is in the numerator, this is in the denominator. And so we get x minus 8 plus 8, which again equals x. So again, we can see that these are indeed inverse functions, because the composite each composite takes us back to the original input value of x. When the inverse of a function is not a function, the domain of the function can be restricted to allow the inverse to be a function. Okay? In such cases, it's convenient to consider part of the function by restricting the domain of f of x. This is saying that sometimes, we looked before and when we did the horizontal test, the horizontal would touch more than one spot, and we knew that the function, the inverse then, would not be a function. And there might be some valuable reasons or valid reasons why we want it to be a function. And so if we limit the domain, the x values of the original function, this could change that. Now, let's look at an example. For example, f of x equals x squared. Well, this is a parabola going up. And of course, the horizontal line touches 2 points on it. Because it's a smile, when we do a horizontal line, we're going to have 2 points. Well, what we can do here, and we can see this when we try to solve for the inverse y equals plus or minus the square root of x. What this means is this is not the equation of a function, because an input of 4 plus or minus the square root of 4 gives us plus or minus 2. Same input, 4, gives us different outputs, 2 and negative 2, SIDO. This is not one-to-one. However, if we restrict the domain of the original function to non-negative numbers, 0 and positive only, then its inverse becomes a function. Because we're saying if f of x equals x squared, but only for x greater than or equal to 0, well, we wouldn't consider any negative values because they are outside the domain. And then we get simply that the inverse function equals the square root of x, the positive square root of x, and we then have two functions. We've made f of x equals x squared into a one-to-one function by limiting its domain to only positive values. And so that's kind of a little trick that we do in math sometimes to solve problems where the inverse would not be a function. Okay, that's our lesson for 5.1. Good luck with the homework and reach out if you need anything.